Welcome to Overfitted, the podcast where we try to make sense of the wild world of AI.
And today we're really getting into something we all interact with constantly, maybe without even realizing the complexity behind it.
Exactly. Speech recognition. We've got a great set of sources here, and our mission is to help you get up to speed fast on how it works, how we measure it, and where it's all going.
Right. Even if you're not deep into the tech side, you'll get a really solid handle on this. It's about turning spoken words into text, evaluating how well that works or doesn't, and looking at the cool stuff being done to improve it.
Okay, so let's start high level. Fundamentally, it's about connecting sound to language, right?
Yep. Two main stages. First, acoustic processing, taking the sound waves from your voice and turning them into, digital features.
And then the second part.
Linguistic decoding. That's where the system uses those features, plus a dictionary and grammar rules, to figure out the sequence of words you actually said.
And early on, this relied heavily on something called hidden Markov models, HMMs.
That's right. HMMs were, and in some ways still are, crucial for the acoustic modeling part, statistically figuring out the sounds.
It's kind of amazing how quickly this tech made an impact. I was looking at this AT&T example from 1992.
Oh yeah, the VRCP system, voice recognition call processing, that's a classic.
It automated operator calls and apparently saved them something like $300 million a year.
A year? Back in 92, that's huge. But it also meant, well, a lot of operator jobs disappeared, around 6,600, I think.
Wow. Yeah, that really shows the economic disruption even early AI could cause.
And it wasn't just cost-cutting, it opened up new services, like AT&T's How May I Help You?
Right. Or that NTT Answer voice banking in Japan. That was even earlier, wasn't it? 1988.
Yeah, imagine accessing your bank account by phone, just talking to it, before the web was really a thing. Pretty revolutionary for its time.
And it hints at personalization, too, like voice control in cars now, recognizing who's driving and adjusting seats or music.
Exactly. Tailoring the tech to the user. That's always been a goal.
Okay, so let's walk through the process when you actually talk to one of these systems today. It starts with ASR, right? Automatic speech recognition.
Yep. ASR is step one. It listens, tries to get the words down accurately, word for word, gives you that written text, the orthographic representation.
But that's just the transcription.
Yeah.
There's more to it for a useful interaction.
For sure. Next usually comes spoken language understanding, SLU. That's about figuring out the meaning, the intent behind the words.
So not just what I said, but what I meant to do.
Precisely. And then you've got dialogue management, DM, which sort of guides the conversation, decides what the system should say or do next based on that understanding.
Okay, let's zoom back in on ASR, the core of it. You mentioned three key steps earlier: acoustic modeling, language modeling, and hypothesis search.
Right. Let's break those down a bit.
Acoustic modeling first. That's about figuring out the probability of sounds, given the audio features. And HMMs are central here.
Exactly. HMMs model the sequence of sounds. Think of each sound, like a phoneme, having different stages of beginning, middle, end. Each stage has a typical acoustic signature.
Yep.
The HMMs, trained on lots and lots of labeled speech data, learn the probabilities of transitioning between these states and the typical acoustic features, often described using Gaussian mixture distributions associated with each state.
So they learn what sound like statistically.
Well, you got it. And that training data is key. You need audio where you know exactly what words were spoken when.
Okay, then language modeling. That's about the words themselves, the sequence, using n-grams.
Yeah. N-gram models look at sequences of n words, often 2 bigrams or 3 trigrams, and calculate how likely one word is to follow the preceding 1 or 2 words.
Based on counting sequences and huge amounts of text.
Exactly. Like reading tons of books and articles to learn that thank you is much more common than thank tree.
Makes sense. But what about word combinations it's never seen before?
Ah, good point. That's where smoothing comes in. It's a set of statistical techniques to assign some probability, even to unseen sequences, so the model doesn't just completely fail when it encounters something new.
Right. And the third piece was hypothesis search.
Yeah, this is where it all comes together. The system uses the probabilities from the acoustic model, how likely the sounds are, and the language model, how likely the word sequences, plus maybe some grammar rules, to find the single most probable sequence of words that matches the input audio.
Sounds computationally heavy.
Oh, it definitely can be. That's why building an ASR system starts with really defining the task carefully.
Like, what words does it need to know? The vocabulary.
Exactly. Vocabulary, the basic sound units or phonemes, how words are pronounced, the lexicon, and any grammar rules specific to the task.
And then you train the models with data.
Loads data. and implement that search algorithm. And often you have to iterate. People keep saying things the system flags as out of grammar. You might need to tweak that grammar definition.
So if we could look inside the recognizer itself, what are the main processing blocks? You mentioned feature analysis.
Right. That's the first step with the raw audio. Feature analysis extracts those key acoustic characteristics. Most commonly, it calculates MFCC's Mel frequency substral coefficients.
MFCC sounds technical.
It is, but think of it as creating a compact numerical fingerprint of the sound every, say, 10 milliseconds. Typically ends up being maybe 39 numbers for each tiny slice of audio.
Okay, so it turns the sound into a stream of these fingerprints. Then what? Pattern matching.
Yep. Pattern matching takes that stream of MFCC vectors and uses the trained acoustic models, the HMMs, the pronunciation dictionary, and the language model to search for the best fitting word sequence.
Yeah.
It's comparing the incoming sound patterns against its learned models.
And then there's confidence scoring. Why is that needed?
Well, the system isn't always perfectly sure. The confidence score is its way of saying, I think this is the word, and I'm 80% confident or 95% confident. It gives a measure of reliability.
Which could be useful. Like if the confidence is low, maybe ask the user to repeat themselves.
Exactly, or flag it for review later.
Let's circle back to those HMMs in acoustic modeling. Why are they such a good fit for speech? You mentioned states.
Right. Speech unfolds over time, and HMMs are good at modeling sequences where you don't directly observe the underlying state, like the specific phase of a phone being produced.
And the Gaussian mixture distributions.
Those model the variability within each state. Even when you're in the middle state of saying a Nessani sound, the actual acoustic features, those MFCCs, won't be exactly the same every time. Gaussian mixtures provide a flexible way to represent that statistical variation.
And training them needs that labeled data and algorithms like Baumwelch.
Precisely. Baumwelch is an iterative algorithm. It aligns the speech data with the current model states, figures out the most likely state sequences, and then uses that alignment to re-estimate the model parameters, the transition probabilities, and the Gaussian mixtures, to better fit the data. It keeps refining the models.
So you can build up complex models. Like a model for the word is would just be the model for the IH sound, followed by the model for the Z sound.
Yep, you concatenate the subword unit models. That's how you build models for the whole vocabulary.
So the key HMM tasks are evaluating likelihood, finding the best state sequence, decoding, and improving the model's re-estimation.
You've got it.
Okay, back to language modeling. N-grams learn word patterns from text.
Right. Counting frequencies of word pairs, triplets, etc. in massive text corpora.
And perplexity measures how uncertain the model is.
Yeah, that's a good way to put it. Low perplexity means the model has a pretty good idea of what word might come next, fewer choices. High perplexity means lots of possibilities, making the prediction harder.
Like the difference between predicting the next digit.
Where the perplexity is just 11, if all digits are equally likely.
Versus predicting the next word in a travel booking system with thousands of words.
Exactly. That ADA system example had a 2,000-word vocabulary, but a perplexity around 20, meaning on average it had about 20 reasonable choices for the next word. Much more complex.
And a bigger vocabulary means more chance of hitting words the system doesn't know. Out of vocabulary words?
Yep, the OOV rate. That
Yeah.
directly impacts performance and increases perplexity.
Okay. Then pattern matching combines all these probabilities, acoustic, language, lexicon, to find the best word sequence.
Right. That's the search process.
Now, what about those simpler, isolated word systems? How do they work?
Those are much simpler. Instead of modeling tiny sound units like phonemes, you build one whole HMM for each word in your vocabulary. So an HMM for yes, one for no, one for balance, etc.
And recognition is just picking the best match.
Pretty much. The system hears the utterance, calculates the likelihood it matches each word model, and picks the word with the highest score. Much easier than continuous speech.
Which brings us neatly to evaluation. How do we measure how well these things actually work? Word error rate, or ER, seems to be the standard.
It absolutely is the most common metric, especially for tasks like dictation or transcription.
For isolated words, it's just the percentage wrong, right?
Simple enough, but for continuous speech, it's a bit more involved. Where counts 3 types of errors.
Insertions, substitutions, deletions.
Right. Insertions are words the system hallucinated added in. Substitutions are where it got the word wrong, replaced it with another. And deletions are words it just missed completely.
And the formula is the total number of those errors divided by the number of words in the correct transcript.
Exactly. Usually expressed as a percentage. So Insertions plus substitutions plus deletions, total words in reference, 100.
We've got some wearer figures here. And wow, they vary hugely.
They really do. Look at something like recognizing connected digits in clean audio can be tiny, like 0.3%, super accurate.
Then you look at conversational telephone speech, like the switchboard corpus. Wears jump up to 20%, 30%, even higher sometimes historically.
It really highlights how much harder spontaneous conversation with a big vocabulary and maybe noise or different accents is compared to a constrained task.
The trend for task-oriented systems is generally downwards over time. Wears are getting better.
Definitely. There's been steady improvement, which is encouraging.
How do machines stack up against us humans?
Interesting question. For very specific, narrow tasks, like those long-digit strings you mentioned, machines can actually be more accurate than humans. Less prone to fatigue or attention lapses, perhaps.
But for general conversation.
Humans are still way out ahead. Our ability to handle ambiguity, noise, accents, disfluencies using context and world knowledge. Machines aren't there yet.
So getting the words right with ASR is just the start. We mentioned SAU spoken language, understanding for meaning. What's the difference between simple classification and true understanding?
Well, a simple system like "How may I help you" might just classify your request into one of a few buckets: billing, technical support, etc. It's matching patterns. True SLU aims deeper. It tries to extract the entities like dates, locations, names, the relationships between them, the core intent, even if you phrase it in an unexpected way. It's closer to actual comprehension,
And that understanding feeds into dialogue management.
which manages the flow of the conversation.
Then spoken language generation to creative response.
And text-to-speech, TTS, to actually speak it back to you. It's that whole conversational loop.
And the user experience depends on all those pieces working well together, not just the ASR accuracy.
Absolutely. Plus the user interface itself. And now we're seeing more multimodal systems too, mixing voice with touch or gestures.
Let's talk about some challenges. Accented speech is a big one. How are people tackling that?
It's tough because accents introduce so much acoustic variation.
Mhm.
One approach is building accent-specific models or using techniques like code books for different accents.
Code book.
Yeah, basically reference patterns tailored to specific accents. Some newer architectures, like modifications to the conformer model, use attention mechanisms that can draw on these accent-specific codebooks to improve recognition. There's research showing decent word reductions with this.
Interesting. What about data augmentation? We hear about that a lot in machine learning. How does it help in speech?
Data augmentation is huge. It means creating more training data by modifying your existing data, adding noise, changing the speed or pitch, maybe reverb.
What do you that?
It makes the model more robust. It learns to handle a wider range of conditions, so it performs better on real-world audio that isn't perfectly clean like the training data might be. It helps prevent overfitting, too.
You mentioned some specific techniques used in speech emotion recognition, glottal source extraction, and silence removal. Could those help general ASR?
Potentially, yeah. Focusing on the glottal source might help isolate the core speech signal. Removing silence could maybe improve alignment, especially in noisy cases. The key is finding which augmentations work best for your specific task and data. Sometimes less is more, sometimes more helps.
Okay, let's revisit were and its downsides. You said it treats all errors equally.
Right, which is a major limitation. Misrecognizing not as now could completely flip the meaning, but it's just one substitution error. Same penalty as swapping a for the.
Or getting a crucial name wrong versus a common word.
Exactly, and it doesn't really handle disfluencies like like if they're not in the reference transcript, the ASR system might be penalized for including them, even if the user actually said them and the meaning is clear.
Like your example, I want to go to the store, might get a worse were than I have to grow, even though the first one is perfectly understandable.
Precisely. It doesn't capture semantic correctness very well.
And if there are issues with just averaging were schools, right?
Yeah.
And comparing across different data sets.
Absolutely. You need to be careful about how you average, especially with files of different lengths.
Yeah.
And comparing words is only really meaningful if the systems were tested on the exact same data under the same conditions.
Using clean public data sets might not reflect real-world noise either.
That's a constant issue. One way researchers try to bridge that gap is by adding noise artificially to clean data sets and testing models across different signal-to-noise ratios, or SNRs. It gives a better sense of robustness.
And what about normalization during evaluation?
Yeah. That's important for a fair comparison. Normalization means pre-processing both the system's output and the reference transcript to make them consistent.
Like expanding contractions, removing punctuation, maybe getting rid of those ums and uhs.
Exactly. So you're comparing the core words, not getting thrown off by superficial differences in formatting or disfluencies.
Good to know people are thinking beyond basic wear, too,
Mm.
looking at things like proper noun accuracy.
Yeah.
You mentioned Gerald Winkler.
Yeah. For things like names, a simple correct and correct score might not be enough. Jero Winkler is a string similarity metric. It gives partial credit if the recognized name is close but not identical to the reference, which can be more informative.
Okay, let's shift to the models themselves. There's a lot of buzz around alternatives to transformers.
Mm.
You mentioned Samba ASR using Mamba, state space models.
Right. Mamba is a really interesting new architecture based on state space models. The big advantage it claims over transformers is efficiency, especially for long sequences.
How so?
Transformers use self-attention, where every part of the input looks at every other part. The computational cost grows quadratically with sequence length. Mamba has linear complexity, so it scales much better to long audio files. Less compute, less memory.
And Samba ASR uses Mamba for both encoding the audio and decoding the text.
That's the structure, yeah. A Mamba-based audio encoder processes the spectrograms, and a Mamba-based text decoder generates the words. It uses a different mechanism than attention, more like a selective state space approach to capture dependencies efficiently.
And the performance, you said state-of-the-art.
The published results are very strong. On benchmarks like LibreSpeech, GigaSpeech, SPGI Speech, some ASR achieve really low WRs, like an average of 3.65%, and particularly impressive scores like 1.17% on LibreSpeech Clean. It suggests these architectures are serious contenders.
Okay, looking ahead,
Yeah.
say 2025, what are the stubborn real-world challenges still facing ASR?
Well, noise is still a big one. Robustness in really noisy places, accents and dialects handling that huge variety smoothly.
Domain-specific jargon.
Yep. Medical terms, legal language, engineering slang, general audls often stumble there. And then there's the whole privacy aspect. People are getting more concerned about voice data collection.
So what are the strategies to tackle these?
Better noise reduction, obviously. More diverse training data capturing more accents, more domains. Techniques like domain adaptation to tune models. For privacy, things like federated learning, where the data stays on the user's device, are being explored. And just being transparent with users?
Building these systems isn't cheap either, right? Data collection, training.
No, it requires significant investment. Data labeling is costly. Training these huge models needs serious compute power. Deploying them efficiently on devices is another challenge.
So maybe using cloud services or outsourcing makes sense for some.
For many businesses, absolutely. Leveraging existing platforms or specialized providers can be much more practical than building everything from scratch.
Wow, okay. This has been a fantastic deep dive. So to wrap up, we've covered the core processes, acoustic and language modeling, the search,
The importance and the limitations of metrics like WEIR,
the challenges like accents and noise, how data augmentation helps.
and these newer, efficient architectures like Mamba emerging with models like Samba ASR.
Hopefully this gives you, our listener, a really solid grounding in understanding speech recognition today.
Yeah, whether you're prepping for a meeting, catching up on AI, or just curious about the tech you use every day.
So here's a final thought for you to mull over. As this technology keeps getting better and weaving itself more tightly into our lives, how do we strike that balance? The balance between pushing for ever higher accuracy, protecting user privacy, and keeping it affordable and accessible.
And beyond that, what completely new applications, what new ways of interacting with technology might be just around the corner, enabled by voice interfaces that are truly seamless and intelligent? Something to think about.
Definitely. Thanks for tuning in to Overfitted.